So, today we're going to talk about a totally new way to think about artificial intelligence. I mean, forget everything you know about training models on these giant static data sets. We're talking about a framework where an AI learns more like a living organism through experience, through evolution, and, well, through pure survival. Welcome to the world of living AI. But to really get what's going on here, we have to start with a kind of strange question. When you think about AI, what comes to mind? Probably vision, right? Like self-driving cars, or maybe language like the chatbots we all use. But what if I told you that AI's most important sense, the one that could unlock everything, isn't one of those? What if it's something way, way more primal? And this slide right here, this really nails the shift. On one side, you've got the AI we all know. It's data-driven, it's disembodied, just code floating in the cloud, and it learns from pictures and text. But on the other side, we have living AI, or LAI. It's driven by experience, it's embodied in a virtual world, and, get this, it's smell first. Yep, you heard that right, smell. And that's the perfect lead-in to our first section, AI's missing sense. We're going to dig into why this ancient faculty is actually the key to unlocking a completely new kind of machine intelligence. I mean, think about it. Biological life didn't start out seeing the world. It started by sensing it chemically. Smell, or olfaction, is the OG sense. So the whole idea behind LAI is to copy that evolutionary path, to ground its intelligence not in abstract pixels on a screen, but in the actual molecules of reality. So how on earth do you teach a machine to smell? Well, the concept is called digital olfaction. The way it works is you take these volatile chemical compounds, the tiny particles that actually create a scent, and you map their unique molecular structures into a kind of digital fingerprint. It's a vector that an AI can finally read and actually understand. Okay, so we know what it is, but how do you actually build one of these digital noses? That brings us right to section 2, where we're going to translate the entire chemical world into a language that AI can finally wrap its head around. The whole process basically breaks down into 3 key steps. First, you digitize the smell, turning those chemical compounds into vectors like we talked about. Second, you feed all that data to a neural network, creating a smell brain that learns the relationships between all these different scent fingerprints. And here's where it gets really cool. Once it understands this whole smell space, it can move to step 3. It can actually start predicting what a totally new molecule might smell like, or even generate the code for a brand new scent. Now, having a digital nose is awesome, but that's just the start. This is where things get truly revolutionary. Welcome to Section 3, Survival of the Smartest, where a concept they're calling digital Darwinism is creating a whole new kind of evolution. And this evolution, it doesn't happen in some boring, sterile lab. The training ground is this incredibly rich, simulated world, like NVIDIA's Omniverse Isaac Sim. Seriously, think of it like a digital primordial soup. It's got real physics, but it's also got simulated chemical emitters, pumping out virtual scents, audio beacons making noise, and even surfaces with different textures for the agents to touch. And inside this world, digital Darwinism just takes over. The AI agents get really simple survival goals. Find stuff that smells like food, and stay away from stuff that smells like poison. The key is nobody programs a solution. Instead, the agents that are just a little bit better at surviving get selected, and their virtual traits get passed on. A solution just emerges, all on its own. And this process is just a constant loop, over and over again. You start with a population, all with random traits. Then you test their fitness. You see who lives and who doesn't. You take the top performers and you let them reproduce, mixing and mutating their traits to create the next generation. And with every single cycle, the agents get a little bit smarter, a little more adapted to their world. But here's the thing, they don't just get generically better. To really adapt, these agents evolve specialized skills, and they do this using a brain architecture called Mixture of Experts, or MOE. You can think of it like our own brains. We have different parts that are really good at very specific tasks. It's the same idea here. And what's so cool about this chart is that it shows this specialization in action. So let's say an agent is out looking for food. You can see its brain activity is just dominated by its food scent expert. That's taking up 55% of its processing power. The other experts, like avoiding toxins or hearing predators, they're still active in the background, but the agent dynamically focuses on the skill it needs the most in that exact moment. This kind of specialization is incredibly powerful, but surviving in a really complex world requires more than just one amazing sense. And that brings us to Section 4, from sensing to thinking. This is where the agents learn to combine all their senses to build a true awareness of what's happening around them. So an advanced agent isn't just smelling anymore. It's perceiving this rich, multi-sensory world. It's processing a chemical signature from its nose, identifying a landmark with its eyes, hearing a beacon with its ears, and even feeling the texture of a surface. It's putting all of that information together all at the same time. But here is the next critical leap. Because simply sensing the world isn't the same as understanding it, right? True intelligence, real intelligence, requires taking all that raw sensory data and actually reasoning about it. And this is done through something called neurosymbolic AI. It's a way to connect two totally different kinds of thinking. The goal, as the source material puts it, is to merge subsymbolic learning, which is that raw, intuitive learning you get from sensory patterns, with symbolic reasoning, which is the world of logic and rules and concepts. It's the bridge between instinct and intellect. This table gives some fantastic examples of how that works. On the left, you've got the raw sensory input, the subsymbolic stuff. An agent smells sulfur and sees rising heat. On the right, you see the logical deduction, the symbolic part. It combines those inputs and deduces, hey, a volcanic eruption is probably happening. It's not just reacting anymore. It's thinking, it's planning, it's anticipating. All of this evolution, this reasoning, it leads us to our final section, which is less about the technical and a lot more about the philosophical. A new form of life? Because when you start building systems that can perceive and adapt and reason in this way, you start to realize something pretty profound. The goal here isn't just to simulate human intelligence. The real goal is to simulate the fundamental processes of life itself. We're talking about evolution, adaptation, and survival. It's about trying to understand the core principles that drive intelligence in any form, not just our own. And this quote, man, it just perfectly captures the whole idea. A traditional AI is trained on a pile of data to do a task. A live-in AI system is dropped into an environment and has to figure out how to live. The learning is constant, it's dynamic, and it's driven by the most basic existential need there is, just survive. And that leaves us with this final question. If an artificial intelligence can sense its world, evolve new abilities over generations, and learn to survive without anyone telling it how, does the word machine even cover it anymore? It kind of challenges our definitions, and it leaves you wondering, what new forms of existence might crawl out of this digital primordial soup?